Namens. That means how to decide sample size from particular strata by using a Neyman's allocation. We got the formula Ni small ni equal small n, that is the total sample size, WISI total divided by summation WISI. WI stand for weightage in ith strata, written as capital Ni upon capital N. So if I replace Wi as capital Ni upon capital N, so the formula will be written as small ni equal small n multiply capital Ni multiply capital Si divided by summation NISI. Now by under Neyman's allocation, what will be the variance of y bar st? Y bar st is unbiased estimator of population mean under stratified random sampling. This we have seen before. This is the original formula of variance of y bar st without allocation. This we derived before. Now I simplify this bracket and this entire formula written as a subtraction of two quantity Wi square Si square divided by small ni minus Wi square Si square by capital Ni. This everything we have discussed in the last lecture. I stop my class by saying that optimum allocation is used to decide the value of Ni. Now see what the optimum allocation says. In this case, we allocate sample size Ni to ith group known as a stratum such that variance of y bar st is minimum for given fixed cost. This is the cost function. C equals C0 plus summation Ci Ni. This is the cost function given, which is fixed. C naught is the overhead cost. Ci is a cost per unit in the survey. Before going ahead, let me explain the difference between Neyman allocation and optimum allocation. Under Neyman allocation, we decide Ni such that variance will be minimum under the condition total sample size is fixed. That is a Neyman allocation. In other hand, if I try to find Ni such that variance will be minimum, but the total cost of the survey is taken to be fixed. So that is labeled as optimum allocation. So I want to decide small ni which minimize variance for given fixed cost. If I try to minimize variance for fixed sample size, that is a Neyman allocation. That is the difference. Let us see how to proceed ahead. We write a function phi, which we have written under Neyman allocation also, variance of y bar st plus lambda time summation ci ni plus c0 minus c. Keep this condition in your mind and see what is a Neyman procedure. Neyman procedure is exactly similar. Phi equal variance of y bar st plus lambda. This bracket is as per condition. Under Neyman, condition is total sample is fixed, and that is equal to small n. So summation ni should be equal to given number n. So if I take this on the left, this condition equal to 0. So 0 multiply lambda becomes 0. Ultimately, I decide ni, which minimize variance under study. So procedure is parallel. Only now bracket I have to change, and that change is due to the condition I want to fix my cost of the survey. So what I do, I take this C on the right side minus C. So when I take this on the right, it becomes a 0. So ultimately this bracket is 0. Multiply lambda is a 0. So phi is nothing but a variance. So we try to decide ni, which minimize the variance with fixed cost. How to proceed ahead? Phi equal summation I1 to k wi square si square upon ni minus summation wi square si square divided by capital Ni. This is your simplified variance formula. Plus lambda, same bracket, continue. Now, according to calculus, if I want to decide small ni such that this phi will be minimum, so we differentiate both sides with respect to ni and equate to 0, you will get answer of ni. Differentiation of first quantity, this quantity, it depends on ni. Summation wi square si square. Here summation will not come because you differentiate at particular I. So it becomes wi square si square, and differentiation of 1 upon ni is minus 1 upon ni square. Be remember. There is no small ni here. That means it is a fixed quantity. Ni is a variable for our case. So differentiation of constant is 0. That's why I put 0. Plus lambda, differentiation of constant 0. You are differentiating at particular I, so summation dropped. Differentiation of ni with ni is 1, so ci will remain. And differentiation of c is 0 again, because differentiation of constant is 0. So you get this step. Now I want to decide small ni, so I will equate this differentiation to 0. Ultimately this equal to 0. So this is the positive quantity, this negative goes on the right hand, so you get lambda ci equal to Wi square Si squared upon Ni square. Take Ci on the right side, Ni square on the left, lambda on the right, so you get this term. Now take the root both side, Ni equal Wi Si root lambda root Ci. Now root lambda is a constant. If I dropped, equal sign become proportional. So what is the relation? Ni is proportional to Wi Si divided by root Ci. And this is your answer of Ni. But here lambda is an unknown constant that is to be decided. Then you get a formula for Ni. How to decide root lambda? It is decided by using a condition of the cost function. We decide proportional constant root lambda such that C equal to C0 plus summation Ci Ni. Replace formula of Ni here, which is in terms of root lambda. Now this Ci, this root Ci gives root Ci on the numerator. Wi Si root lambda. When the subscript I is there, that means it is a variable quantity with this summation. But here root lambda is a pure constant. So you take this on left and this left on the right. So you get a value for root lambda. Put this value of root lambda at this point. So you get result for Ni under optimum allocation. And that answer turns to be like this. Wi Si root Ci. And there is 1 upon root lambda. So this reverse C minus C0 summation Wi Si root Ci. This is the formula of Ni under optimum allocation. After getting Ni, you can proceed for getting a variance under optimum allocation. And the formula of variance of y bar st original without any allocation is this minus summation Wi square Si square upon Ni. There is no change in the first step because there is no Ni, small ni. Now what you derived here, you put this formula at this point as a reverse. The scan copy is not correct, just replace this Ni means this formula. So this comes numerator, this comes down in the formula. So I have finally summation Wi square Si squared upon Ni minus summation Wi Si root Ci square is there divided by C minus C naught. This is nothing but optimum allocation to get Ni and respective variance. And that completes your chapter under the heading of stratified random sampling. Today we'll stop at this stage. We'll start a new chapter under the heading of systematic sampling next time that I will tell you. If you have any doubt to clear, you can clear it.